Hi, welcome back. In this video we take a deeper, more theoretical look at circular motion, and we limit our discussion to a very particular type of circular motion, uniform circular motion. Uniform circular motion is simply circular motion in which the speed of the object is constant and the radius of the circle being traversed is also constant. So that's very important. In uniform circular motion, the speed of the object moving in a circle and the radius of the circle are both constant. You're going to find, at least in this course, that most problems involving uniform circular motion can be modeled as simply a particle going around in a circle, as we have here. So this particle could represent, let's say, the skid going around in a circle here, or this ball going around in a circle. So it would be a view from above now, or this car moving along this little dip in the road. We could also be talking about this car going around this curve, or a planet like the Earth going around the Sun. What we have here are vectors representing the velocity of the particle at different points in time. So again, this particle could be representing a planet or a person on a skateboard going around a loop. What is important to note is that the magnitude of these vectors doesn't change, but the direction changes. So strictly speaking, these labels, this should be labeled velocity 1, this should be velocity 2 perhaps, and this should be 3. Because obviously these vectors are not the same. They have the same magnitude but different directions. So the velocity is obviously changing, which means then that this particle is accelerating. Of course, if it's accelerating, in what direction is that force acting? So let's take a look at the particle when it's right at this location. Let's suppose the net force acting on the particle acted in this direction as shown here. Could such a force be responsible for the uniform circular motion of this particle? Well, the answer is no. This force would have components along the y and the x directions, as we see here. So this component, yes, this component would make the particle change direction, but this component would make it speed up because this force is in the same direction as the motion at this point in time, and we have stipulated that the particle is moving with a constant speed. So obviously this orientation will not work because not only will it change direction, but it will also travel with a greater speed due to this component. How about if the force acted in a direction like this? Well, we have the same problem. We have these components. Once again, we have a component that will force the particle to change direction. But here we have this component now, which would be what? Slowing down the particle. And again, we're talking about uniform circular motion. So this direction won't work either. Of course, if the net force acted in this direction, then there would be no component in a direction of the velocity at this point in time, so this particle would neither be slowing down nor speeding up. All that this force would be doing is it would be changing the direction of travel of this particle. So when the particle is here, the net force acts in this direction. When it's here, the net force acts in that direction, always perpendicular to the velocity of the particle. And here, the force again acts perpendicular to the velocity. So this should be pointed right to the center, right? The net force, the centripetal force is always pointing towards the center of the circle. Let's look now at a new way of defining the position of this particle. Before this, you defined the position of a particle by giving its x and y coordinates. But if you know the radius of this circle that is being traversed by this particle as it goes around in a circle, you can simply give its position by giving this angle, measured say from the x-axis. And so that's what we want to do here. When we express the position of a particle using this angle, we say that we're expressing the angular position of the particle. And so we define the angular position to be positive when measured counterclockwise from the positive x direction. Now you're probably used to expressing angles in degrees, but we now need to look at a different way of expressing angles. We're going to express angles in radians. And in radians, an angle is defined as the ratio of the arc of the circle traversed to the radius of the circle. And so this angle then is equal to the ratio of S to R. So S is the arc of the circle. Notice this is going around and around, and so this is the arc of a circle. This is the radius. And so the angle is defined as the ratio of this length, the length of this arc, to the length of the radius. Now, you know that for one complete revolution, the arc is the circumference, and so the circumference of a circle is 2 pi r. So S would be 2 pi r, which means then that you would have 2 pi r divided by r, which would give you 2 pi. And so then a complete revolution corresponds with an angle of 2 pi radians. In other words, 360 degrees is the equivalent of 2 pi radians. Notice the unit per se is the radian, not pi. Pi is just a number. Remember that pi is just a number, approximately 3.14. Of course, for half of a revolution, then the length of the arc would simply be pi r. And so if we divided pi r by r, we'd get pi radians. And so in radians, an angle of 180 degrees is pi radians. So this gives us a very useful constant ratio. And that's this, that the ratio of any angle expressed in degrees to the same angle expressed in radians is a constant and equal to 180 divided by pi. So this is a very useful ratio that we can employ to convert between degrees and radians, or vice versa. So let's look at a few examples. So here we have to convert 56 degrees to radians. So we simply make use of this ratio here. We know that 56 degrees over x radians, and we can just write rads like that, would be 180 degrees over pi radians. And so some basic algebra here then gives us that x then is going to be equal to 56 times pi over 180. And this gives us 0.98 approximately radians. Okay, so now let's look at another example. So we need to express 48 radians in degrees. So it's the same thing. We want to know how many degrees. We have 4.8 rather, not 48, 4.8 radians. And then that's going to be 180 over pi. And so x then is simply 4.8 times 180. So this should be very simple algebra. And that gives us 275. And so 4.8 radians is 275 degrees. Let's look at the previous problem briefly. Here I shouldn't have written radians here. X is 0.98. I already have the radians here, so let's just fix that for all you purists out there. So x is 0.98. So 56 degrees is 0.98 radians. If I didn't put radians here, then I could call this radians here. So let's look at another problem. Very often it is convenient to express your angle as a multiple of pi radians. So if we have 34.7 radians and we want to express this as a multiple of pi, that's simple. We simply multiply this by 1, but we do so cleverly. We say 34.7 radians is equal to 34.7 times, and notice this little trick. Later on we'll find a shortcut. So notice, as long as I multiply by 1, I know this has to be the same as this. Of course, I can rewrite this as 34.7 over pi times pi radians. And then I just say, well, 34.7 divided by 3.14. Or if you have this in your calculator, you just press the button. And so this gives us approximately 11 pi. Don't need to put the multiplication sign again. And so you see what we do here. We simply divide by pi, and now that's our answer expressed in radians. So if I have, say, 63 radians, I can say, well, simply 63 divided by pi radians. Of course, 63 divided by pi is 20.1 more or less. And so this is a very helpful little skill to have. So let's look at one more problem here. Very often we want to express an angle as a multiple of pi radians, but between 0 and 2 pi. Why is this? Let's suppose we have a particle that goes around in a circle, and it goes around 360 degrees, and then it goes, let's say, 90 degrees more. So then that would be 450 degrees. But the angular position of something that goes around 450 degrees, well, that's similar to going around just 90 degrees in the sense that the angular position of the particle is the same. So the angular position of 450 is equivalent to an angular position of 90. And so basically, when we want to talk simply about the angular position of a particle, we usually talk in terms of an angle between 0 and 360. So 450 would be the same as 90. So let's take a look at this then. We have 432.8 radians. There are different ways to solve this, but one easy way is to simply express this in terms of pi. So we say that's going to be approximately 137.76 pi radians. And then we simply subtract the biggest whole number out of this. So if we take away the biggest whole number, which would be what? 136, that leaves us with, so this now would be equivalent to 1.76 pi radians. So let's make sure you get this clear. This is the same as saying 136 pi, which is 68 complete revolutions. So if you go, remember every 2 pi is a complete revolution, so that's 2 pi, 4 pi, 6 pi, 8 pi, until you get to 136 pi, and then you go 1.76 pi. And the nice thing about this way of expressing the angle is that you know that between here, this is 0, this is pi over 2, this is pi, coming here it's 3 pi over 2, but that's 1.5 pi, and of course then we're here to 0 or 2 pi. So obviously if this is 1.5 pi, right, so it's 3/2 is 1.5. So this angular position places the particle somewhere in here, between 1.5 and 2. So that's the nice thing about expressing angles as a multiple of pi, but between 0 and 2 pi radians. It's easy to see the angular position. So looking at 432.8 radians, you can't really visualize the angular position, but 1.76 pi radians, it's easy to visualize where it is, somewhere in this quadrant. Okay, so that's it for this video.